Hi friends, this is Rashekar, a GET faculty for electrical machines. Today in this video, we are going to discuss about parallel operation of transformer. Parallel operation of transformer. First of all, why we are going for parallel operation? What are the features of parallel operation? What are the advantages? First one, we can improve the load capacity due to parallel operation. Load capacity increases. Load capacity increases. Second one, reliability increases. Reliability increases because in two transformers, if any one transformer under faulted condition, remaining transformer will serve the load continuously. So reliability increases and efficiency also increases because two transformers operates at nearly full load condition. Two transformers operates at nearly full load condition. So load capacity increases, continuity increases, efficiency increases, and standby transformer cost is very less, and future requirements like that, many advantages are there for parallel operation. For example, I have two transformers. In future, load decreases, so one transformer is disconnected from the parallel operation. Only one transformer will serve the load. Like that, many advantages are there. Mainly capacity increases, continuity increases, and efficiency also increases. This is the features of the parallel operation. Now, what are the conditions for parallel operation? What are the conditions to operate the transformers in parallel? To operate the transformers in parallel, what are the conditions for parallel operation? In that, first one, polarity of two transformers should be same. Polarity of two transformers should be same. Polarity of two transformers should be same. I said you already in polarity test. Sir, if two transformers polarities are not same, then what happened? Otherwise, if polarities are not same, otherwise dead short circuits will take place. Dead short circuits will take place. Dead short circuits will take place, which damages the machines. This is first most very important condition, polarities. And next one, the second condition, the terminal voltages should be same. Terminal voltages should be same. And the third condition, voltage ratios should be same. Voltage ratio should be same. Voltage ratio should be same and terminal voltages also should be same. Otherwise, if the voltage ratios are terminal voltage not same, otherwise what happens, sir? Otherwise, circulating currents increases. So what, sir? If circulating currents increases, what happened? If circulating currents increases, temperature increases, losses increases, efficiency decreases, and windings may damages. Due to high temperature, windings may damages, failures of insulation, failures of insulation, like many disadvantages are there. If the voltage ratios and terminal voltages are not same, then otherwise circulating currents increases, which leads to temperature increases, losses increases, efficiency decreases, and failures of insulation will take place. Failures of insulation. This is simply about the second and third conditions. And next, the fourth condition. What is the next condition? The next condition is very, very, very important. This is also very, very, very important. The X by R ratio should be same. X by R ratio should be same. X by R ratio should be same for two transformers. Sir, if X by R ratio not same, what happens, sir? If X by R ratio not same, two transformers operates at different power factors. Different power factors. Two transformers operates at different power factors. This is also a difficult thing. And the last condition here in parallel operation, the last condition, the load KVA, the sharing load KVA should be inversely proportional to impedance. The KVA is inversely proportional to impedance, or the KVA is directly proportional to per unit impedance. The per unit impedances should be same. Simply the per unit impedances should be same. Per unit impedances should be same, or the KVA inversely proportional to impedance, or KVA directly proportional to per unit impedance. Based on per unit impedance, our loads will sharing. Our transformers will share the load based on per unit impedance. If this is not possible, if the fifth condition is not possible, what happens, sir? If the fifth condition is not possible, otherwise, load sharing is difficult. Load sharing is difficult. Load sharing is difficult. Load sharing difficult, nothing but one transformer overloaded. How the transformers share the load? Let's see here. For example, two transformers operating in parallel. Two transformers, right? For example, two transformers operating in parallel to the load. These two transformers operating parallel to the load like this. This is my load. This is my load. For example, this is my load. See here, this is my load. This is a phase and neutral because of single phase transformers. This is transformer A, for example EA, and this is transformer B, EB. Here the current is IA, and here the current is IB. This is the line current or load current, and this is the terminal voltage VT, terminal voltage V simply. These two transformers operating in parallel. Yes or no? Now tell me, what is EA? EA is equals to, generally EA is equals to V plus IARA plus J IAXA, because this winding having RA and XA, this winding having XB and RB. And what about EB? EB is equals to V plus IB RB plus or minus or plus IBXB. This is simply the EMF equations. Or simply we can recognize V plus IAZA and V plus IAZB. This is the equations. Now, according to current dividend rule, IA is equals to, according to current dividend rule, IA is equals to, tell me, IA is equals to the total current multiplied with opposite impedance ZB upon total impedance ZA plus ZB. And the load sharing or the current in the second transformer IB is equals to the total current IL multiplied with opposite impedance upon total impedance. This is the current sharing by two transformers multiplied with the voltage on both sides. So tell me, what is here? EA IA is equals to V into IL ZB upon ZA plus ZB. EA IA nothing but the load shared by transformer A. The load shared by transformer A is equals to total load KVA multiplied with ZB by ZA plus ZB. This is the load shared by transformer A. Similarly, the load shared by transformer B is equals to total load KVA multiplied with ZA by ZA plus ZB. This is also important. They will ask you questions on this formula, gate questions on this formula. Load shared by transformer B and load shared by transformer A. This is simply the load sharing in parallel operation. Load sharing in parallel operation. In this parallel operation, we have three cases. In first case, if voltage ratios are same, nothing but EA is equals to EB is equals to E, and X by R ratios also same. If X by R ratios is same, nothing but power factor same, angles is same. In case 2, voltage ratio same, but X by R ratio not same. And in case 3, voltage ratio not same and X by R ratio not same. Let's see how the vector diagrams. See here, first for this is for example voltage V, and this is my IA, and this is my IB, because this is phi A and phi B, both are same, both are in phase to each other. Phi A and phi B same, so now IL, the load current, is equals to arithmetic sum of IA and IB because in phase to each other. Now we have to calculate EA and EB. EA and EB both are same, right? So calculate here. First, for IA, this is IARA. Of course, same for IB. This is also IBRB. This is also IBRB, which is in parallel to the I. Next, for 90 degrees, right? Next, in 90 degrees, this is IAXA. Of course, this is only IBXB. Now, this V plus this IZ is equals to EA, and that is equals to EB, and this is equals to E. This is the vector diagram when the voltage ratio same and X bar ratio same. But here, see, this is somewhat different. Here, this is somewhat different. Let's see here, clearly see here. For example, this is V, and for example, this is my IA with some angle theta A. But theta B is different. This is IB with some angle theta B, phi B, power factor angle B. Here, the X bar ratios are different. But I want the load current. The load current is vector sum of these two. The load current is vector sum of these two, because these are the two vectors are different displacement. Now let's draw the vector. Here IA is there, so this is my IA RA, and my IB is there, so this is my IB RB, and perpendicular to IA IA XA, and like this is IB, right? This is IB, right? So perpendicular to IB, this is IB XB. Of course, the sum is EA, that is equals to EB, that is equals to E. Again say, because I said you already the voltage ratios are same, but the phi A, phi B's are not same, even though the voltage ratios are same. So the vector diagram is like this. So IA, IARA, IB, IBRB, IBRB, and perpendicular to this IA and perpendicular to this one, then we can get the answer. Okay, so then we can get the answer. This is for IA and this is for IB. Now let's go for third one. That is completely different, right? Let's see. For example, this is my voltage V. Here, this is my IA and this is my IB. Of course, vector sum of these two is taken as IL because out of phase. Now IA is there, IARA should be there. This is IARA, and perpendicularly IAXA, and this is EA. EA is completed. Now IB is there. For IB, this is my IBRB, and perpendicularly IBXB, perpendicularly IBXB, and this vector is EB. This is completely different. EA, EB not equal, phi A, phi B not equal. EA, EB equal, but phi A, phi B not equal. EA, EB equal and phi A, phi B equal. Like this, different vector diagrams for parallel operation of two transformers. Okay, so you have to remember the conditions. First one, polarity, otherwise dead short circuits. Next one, terminal voltage and voltage ratio, otherwise circulating currents. Next one, X bar ratio, otherwise different power factors. And next one, and last one, kVA. What is that? kVA inversely proportional to impedance or directly proportional to per unit impedance. Otherwise, load sharing will difficult. Load sharing difficult, nothing but one transformer overloaded, other transformer underloaded, and power factor also decreases. Remember this. If the kVA directly proportional to per unit impedance not possible, power factor also decreases. Power factor also decreases. The load sharing is mainly depends on per unit impedance. If the per unit impedance is same, then load sharing also same. Very important words. This is about the parallel operation of transformers. Okay, thank you.